Well, welcome back. We'll have a sequence of 3 talks in this session. The first will be by Ken Stephenson on the rigidity of circle packings. Ken?
It's certainly a privilege to speak here, and I want to thank the organizers. It's going to be wonderful to hear the stories. Each of us has our modes of interaction with Oded. I was not a direct co-author, but talked with him many times, and I'm looking forward to seeing those various gems that we're used to seeing come out of his work and conversations with him. And one of those is what I'll be talking about today. I'm talking about circle packings. And I think that circle packings, if you look at the record, have a solid claim on Oded's affections early in his career. And we talk about beauty in mathematics in various ways. This is maybe a superficial one, but I can't get over the lovely pictures you see in circle packing. A Doyle spiral. This is one of Oded's square grid packings, a couple different versions of the error function, early stages of developing an error function discretely. This is a conformal welding using circle packings. Another connection with Oded's work is the squared rectangle on the left and the circle packing version on the right. Same combinatorics and more or less the same rectangle. And just in general, the number of ways in which circle packings appear in the study of conformal structures. And that's sort of the underlying theme here. And with Oded's work on circle packing was the connection with conformal geometry. And so I'm going to give just a little background, because I know that not everyone knows about circle packing or knows the basis of it or potentially what it contains. And so just the basic definition, a circle packing is a configuration of circles with a specified pattern of tangencies. And as with everything that Oded worked on, there are variations. We might be working in a Finsler metric. We might be working with overlapping circle packings. I'm going to stick with tangency patterns. And so the idea is that someone comes up and gives you a combinatoric situation, purely combinatoric, like a triangulation. And then there's this theorem, and we'll quote a couple theorems on the existence of circle packings having those combinatorics. So I'll start with the sphere, which we're going to work on mostly today. So here I've used a random point process to put points randomly on a sphere, and I've taken the Delaunay triangulation of those points. So this is what I would call a random triangulation of the sphere. And now every triangulation of the sphere has associated a circle packing. The color coding is just about the degree, so there's nothing special about that. It's a little prettier sometimes. But the point is that with every vertex in the triangulation, there's associated a circle. And if 2 vertices are connected by an edge, those circles are required to be tangent to one another. And so what happens is an arbitrary combinatoric situation is given a geometry by being required to fit together with these circles. And so the circles change the geometry, but respect the combinatorics of the original pattern. And so we're going to talk about the basic existence and uniqueness results. Just to get started, so the first result is the Kerba-Andreev-Thurston theorem. As Bill Thurston told me one time, and you'll have to check with him whether he still says this, he proved this in the morning, found a proof in the afternoon that from Andreev's work, But then it was several years later that it was found to have been proven by Kerba back in the 1930s. So that says that given any triangulation of a topological sphere, there exists a univalent. So univalent simply means that the circles don't overlap. There's a univalent circle packing of the Riemann sphere having the combinatorics of that triangulation. And what we're going to talk about is the rigidity, which is a sort of uniqueness version of things. So moreover, this packing is unique up to Möbius transformations and inversions. And we're going to cut out inversions. We're going to think of oriented objects. So given the triangulation, there's a rigidity here, and that you get a circle packing associated with it, and it's unique up to Möbius transformations. Now that's been extended considerably. So the more general theorem is, given a triangulation of any topological surface, there exists a conformal structure on that surface, making it a Riemann surface. And there's a univalent circle packing in the intrinsic metric, the constant curvature metric for that Riemann surface, that fills. So that's a little technical thing in the disk. You don't want to be shrunk down. So you want to be sort of a maximal packing in that Riemann surface. So given any triangulation, the surface might be compact, open. The triangulation might be finite, certainly in the compact case, or infinite, with boundary, without boundary, etc. Given any triangulation of an oriented surface, you can put a structure on it and a circle packing compatible with that structure in the surface. And again, there's a uniqueness statement. The conformal structure is uniquely determined by the combinatorics. And the circle packing is unique up to conformal automorphisms of the surface. So these are the uniqueness type of results, the rigidity I want to talk about. And the upshot for me is that circle packings come along and they take a purely combinatorial situation and endow it with a geometry. And the important thing to understand is that this is not just any geometry. It has the local rigidity, which is the sort of localized version of the rigidity globally we're going to talk about. And if we allowed ourselves to move off the sphere and put some boundary in or allow some branch points, we have a global flexibility. And in my mind, it's this interaction of the flexibility globally and the local rigidity, which puts it sort of in the category of analytic function theory, which is where I came from. So we all like to recast things in our own favorite way, but to me, this is where conformal geometry comes in. And so this is a particularly familiar geometry that we get. And I call it discrete conformal geometry. And that's where Oded's work started, in proving the uniqueness and existence of these packings and studying the relations between the discrete geometry and classical conformal geometry. The next speaker, Zheng-Xu He, will be speaking more about this. And so what I wanted to do was to talk about how this came up. Talk about how this came up and actually do a proof. So the setting was this. Bill Thurston suggested that if you take a region omega and you fill it with a circle packing, and then using Kerba's theorem, you repack that in the unit disk, that from this, the mapping between these two regions, so you put this circle packing in here. Now this has the same combinatorics. So this is a circle packing with the same neighbor relationships. And we have now a map between the unit disk and our original region omega. And Thurston suggested that this was a discrete conformal map, or I think he called it finite Riemann map. And so the theory developed around studying the conjecture, which was that under refinement, that is, if you fill the region with smaller and smaller circles and increase the complexity and do these maps and appropriately normalize, they will converge in the limit to the classical conformal map of the disk onto omega. Now this was proven shortly after the conjecture was made by Roden and Sullivan, and it's been vastly extended to other situations, other combinatorics in particular. And a lot of that work, in fact, is Oded's work on more general combinatorics, for example. But sort of a catchphrase is that under refinement, objects in the discrete world of circle packing invariably, it seems, converge to their classical counterparts. So if you build something discretely that looks like a classical object and you refine it and keep it looking like that classical object, it will actually converge to it. So it's somehow capturing the same geometry. But what I want to look at in particular, there are a huge number of papers, I'll list some at the end, of aspects of this that Oded worked on. But I want to talk about a particular result. And so it's the KAT theorem here, the Kurban-Andreev-Thurston theorem, but it generalizes beyond that case. But I'll prove that. So the claim here is that if I have a circle packing of the sphere like the one pictured, call it P, that any other circle packing of the sphere with the same combinatorics, same number of circles, same neighbor relationships as this one, will in fact be a Möbius image of it. So that's uniqueness. And the crucial tool in this is a very deep result, which is why I'm presenting this, because some people may not realize this, that two circles can intersect at most 2 points. So we'll exploit that deep property. So we can actually pretty much prove this whole thing here. So the setup, part one at least. So we have our packing P. I'm going to identify a mutually tangent triple there. And I'm going to take my competitor, my other packing. I can't draw it because, of course, it's just P. But we have a presumed competitor packing, and I identify combinatorially the same triple. And with a Möbius transformation, I can get that triple of circles to be the exact same triple of circles as in P. So I've normalized things, and that's where the Möbius transformation ultimately is going to come in. I have to show the rest of the circles on the right are the same as the circles here. And I'm going to presume that the very next one, that fails to be the case. So here's one sort of extending that triple, a neighboring circle. And in the competing packing, that neighboring circle is a different size. This doesn't happen. They have to be the same. So that's the first part of my setup. Now I just put the infinity inside that interstice, and I project both these packings down to the plane, and I get juxtaposed configurations. Now I've drawn the circles for one of them, but the other circles are in there as well for the other packing. So everything's now inside this interstice with the two circles that differed, the red and blue there, as shown. One more small adjustment. I'm going to take the packing with the blue circle, and I'm going to scale it away from A just a little. And so we end up in the situation on the right there. So I have these two packings with the same combinatorics in that situation now. And it's that collection of circles that I'm going to study a little more. So let's focus in on a small patch of this packing. And I'm going to identify what I call the elements, for lack of a better name. The elements of the packing are, well, the circles. So every circle is an element of this packing. And the interstices. So every interstice is an element. Throw those together, I have E, the collection of elements of this packing. Now, there's another packing around, which in this region looks like this. You can see sort of which circles are identified in the combinatorics, but they're shifted from one another. And so we have a collection of elements for this other packing, E prime. And in particular, we're going to look at the triangular elements, I'll call them. These are the interstice elements. And the interstice elements in the two competing packings here are shown, corresponding elements. And the dots represent the tangency points of the circles, and those are identified from the blue to the red, you know, which of those dots corresponds to the other in the other packing. So what we're going to do now is compare these elements. And somehow, I don't know exactly how Oded did this when he first saw this. He had a sort of hands-on approach, as I think is common. He did not look over the literature and try to find something that did his work for him. He just dug in. He knew it was true, and he figured out a direct method of showing it. So he came up with the notion of compatibility. It's not the same as here, but that was the genesis. We're going to use a fixed point index. So I'm going to assume that I have two simple curves, the red and the blue, gamma and sigma. And I'm going to define a homeomorphism between these two curves. I'm going to set up this little terminology. So this is a fixed point free homeomorphism, orientation preserving between these two curves. And I'm going to define the index. And I think it would be appropriate maybe to just explain what this index is. So I actually have blue and red here. This is a very simple case, and so of course the interactions could be more complicated. But I have these two curves, and I'm going to take a function which maps each point on this curve to some point on the other curve. In the picture, I start with these points of intersection. And let me describe this index in a very simple way. Suppose that your friend is walking around gamma, and you are walking around sigma, and you have an elastic string between you. As you walk around, the only requirement is that you not both be at one of these intersection points at the same time. That's the fixed point free. The other requirement is, as your friend walks in the positive direction, you move in the positive direction. And the winding number is at the end of the day whether that string winds around you when you get back to your initial points. So your friend walks around one curve, you walk around the other. And what's the purpose of the function? Well, the function says that I, on my curve, get to choose how to walk around that curve and try to control that winding. So given the curve gamma, I might be able to specify a function which tells me how to walk around the curve sigma so that the winding has a certain property. And that's what we're going to use, is that winding number. So, compatibility results. If you have two circles as your curves, because they can only intersect twice, it's not difficult to show that every fixed point free homeomorphism has an index that's greater than or equal to 0. Okay. So there's no way that you can fail, no matter how you choose to walk around your path compared to your friend on the other path. The index is always greater than or equal to 0. It's a little more complicated on these interstice elements, but the basic idea is that in addition to the conditions on the map being a fixed point free homeomorphism, we're also going to require that when your friend is at A, you're at A prime. When your friend is at B, you're at B prime. And when your friend is at C, you're at C prime. So that compatibility. And then the theorem is that given these two topological triangles, there exists a fixed point free homeomorphism with index greater than or equal to 0. And that's actually fun to figure out because it's a very straightforward, simple arguments to get this done. You can teach this in an honors undergraduate course. It's a lot of fun. So here's the proof. For every interstice element, that's the triangular ones, we choose a map between the element in P and the corresponding element in P prime. And by the previous slide on the right-hand side, we're able to choose that by force to have index greater than or equal to 0. Now on the circle elements, it turns out that your map is already defined because every circle, the boundary is covered by interstices, by edges of interstices. And for each of those interstices, you've already defined a map to the corresponding edge of the interstice in the other packing. And so this already defines a map on the circles. And so you have maps on all the elements now. And by the way, this in our overall configuration, there are some interstices around the boundary. And so this defines a map on those, the outer boundary there, because those edges are not shared by any other interstices. So they're sort of left over, and there's a induced homeomorphism, fixed point free, on the outer boundaries of the configurations. So now we throw together this sum and take about account of cancellations. Because when you're doing a winding number, it's a change in argument. And if you're on an edge of an interstice that's shared with a circle, the change in arguments, when you're thinking of it as a triangular element, is canceled by the change in argument because of orientation when you think of it as part of the neighboring circle element. So everything inside gets canceled. This is a familiar argument to most of us, but the result is that this index induced on the boundary is greater than or equal to 0. But there's the boundary. All the edges of interstices and the circles and the elements inside have been taken care of. And we have this homeomorphism on the boundary. And if you just isotope that, it's this configuration. And it's very quick to see that the index is -1. Just go around here. A has to go to A prime, B has to go to B prime, C has to go to C prime, and D has to go to D prime. So it's a negative winding, and we're done. Competing packing fails, and we have uniqueness. So to me, personally, this is the prettiest proof I know, pretty much in mathematics. Now, it's all very elementary, and it shows you an amazing result. It applies further than just triangulations of the sphere. It shows, for example, that circle packings that fill the plane are unique, and that's where the proof of Roden and Sullivan depended to get this whole topic going. So that's the proof. And I want to say a little more, though, about where this leads. So let's put a book into the conjecture that started this topic for a lot of us, Thurston's conjecture about these conformal maps, because Oded and Zheng-Xu have proven by further study of the distortion of these circle packings, the local rigidity, that the Kurban-Andreev-Thurston theorem on circle packings of the sphere actually implies the Riemann mapping theorem for plane regions. So there's no higher accolade for a complex analyst than to say you have a new proof of the Riemann mapping theorem. Okay. And a final word about other topics. There are too many, I didn't want to rush through them, but here's another example of something that that Oded saw, which I really still can't quite believe, although I've studied the proof and it's true. So here is one of my favorite packings. It's a heptagonal packing. Every circle has 7 neighbors. There are infinitely many generations of circles here, all in the unit disk, all actually the same hyperbolic radius. So I'll take this just as an example packing, infinite hyperbolic packing. And I can sort of repack that in the square. So that's the same combinatorics. But of course I'm lying to you. There are not infinitely many circles either place. And I actually don't know if that packing if I can construct that packing in reality, but I've gotten close enough for government work. But they have a theorem, Schramm and He again, have a theorem that given any Jordan domain, there exists a univalent circle packing with these combinatorics which fills that region. So not just a square, but any simply, take your most horrible Jordan curve, you can fill the inside with a packing of these combinatorics where every circle has 7 neighbors. I just can't imagine that, and in fact I can't construct them. It's not a constructive proof, but it would be appropriate maybe. By the way, there's another uniqueness result here. It'd be appropriate in the circumstances, however, to be able to pack a simply connected region like this theorem allows. So there's one that I suggest I'd like to see, a packing of that with every circle having 7 neighbors. Okay, here's some of the papers to indicate Oded's early work on this topic. It's just gorgeous stuff. As so as said earlier, you just enjoy reading these. And often I think you, if you're lucky, you see the idea and the extra stuff that has to be imposed later doesn't bother you. Those ideas are really in there. So thanks to you and thanks to Oded.
Are there any questions? Stephen?
Well, I don't have a question, but I rather have a comment. As Wendelin already said, Oded wouldn't just settle for one proof, but he produced several usually. And this is the most important theorem almost about circle packing, and so accordingly he actually produced maybe like 5 proofs. And the one you presented, that's probably the most important because, as you said, it applies also to infinite packings, and it's very, very beautiful. But one proof I actually found that I wasn't aware of. I found only very recently when I prepared that overview article. And it's not published, I think, and I found it actually on Wikipedia. So we don't know. But that was a very, he really was a very, he loved to contribute to the Wikipedia. And he contributed also a lot to the circle packing on Wikipedia. And the proof that is on there is so short and so beautiful and so elegant that you wouldn't believe it. I thought it must be false. Yeah? And then no, really, it is. It's very, very short. Maybe I'll present it tomorrow. But then I wasn't quite sure. It definitely had Oded's handwriting all over it, yeah, because there was no credit, no nothing. So I tried to research a bit more, and then I went to the, when you see the history file, who contributed. Of course, there were a lot of Oded's entries. And I wasn't so sure. I just put in my article, I believe that this proof is due to Oded. And then I got some comments, and with Don Marshall, we actually chased it down. We looked at every date with all the entries. I think this is, it's an incredibly short, elegant, like 5-line or 3-line proof of the rigidity in the finite setting. Anyway, sorry.
Well, can I keep this as my favorite anyway? I have to see it first. Yeah.
No other questions or comments?
If I could say one more thing, my last correspondence with Oded was about a year ago, and I'm working on some random triangulation stuff, and I suggested something about convergence, sort of random convergence to conformal structure, and the reply was, certainly seems like it could be true, but it looks very hard to prove. And so, needless to say, I've moved on to other things. Because if his insight didn't really convince him, and he said it was hard to prove, I think I'll take his word on that.
Any other questions or comments? Let's thank the speaker again. And we'll take a quick break of about 3 minutes. The second talk in this series of 3 on circle packing will be given by Zheng-Xu He. He'll speak about disk packings and conformal maps.
Okay, thank you. So it was really a hard choice for me. There were so many things to choose to choose to talk about when I was invited to talk here. Anyway, finally I came down to talk about just one proof. Let's see. So basically, this is built on what Ken has already described. So the relationship between circle packings. So we want to call it disk packing for simplicity of definitions. Disk packing and the conformal maps. So basically, how disk packings can approximate conformal maps. So here was the original theorem. Actually, Thurston's conjecture that was proved by Roden and Sullivan. So basically, we have two disk packings, one in any domain and the other one in a unit disk. So basically, the theorem says, what the theorem says is that the one-to-one correspondence between disks in one packing to disks in another packing approximates a conformal mapping. So basically, we have a few. Anyway, this is the full statement. Let's see here. So we have two packings, one in an arbitrary domain and the other one in the unit disk, and we have some conditions. Those are basically some trivial conditions that so on the boundary disks, basically we want the disk packing to fill the whole domains. And also the third condition is a normalization condition, so that the limit packing will not push toward the boundary. So under those conditions, a subsequence of f sub n, which is basically the correspondence map, so a subsequence of f sub n should converge locally uniformly to a Riemann map. So there are a few problems. So the first one is to show the limit map is a conformal map. And this was achieved first achieved by Roden and Sullivan, and they proved the rigidity theorem. This is by itself a very interesting theorem, rigidity theorem of infinite hexagonal packing. So basically, if you have another packing, if you have any infinite disk packing in the plane that is combinatorially equivalent to the infinite hexagonal disk packing, then all disks of the packing must have identical radius. So this is a very beautiful rigidity result. So the argument goes, so if you have a disk packing, as in the picture here, so you can take limit here. And the limit packing, as n goes to infinity, must be a regular hexagonal packing. So all circles in the limit should have the same radii. So as a consequence, the limit mapping must be conformal. So this is basically a consequence of the rigidity theorem of infinite packing. Now, so the argument was only good for C0 convergence, and that uses actually quasi-conformal maps, convergence of quasi-conformal maps. And also, you need bounded valence as to be able to take limit. So actually, I want to do a small digression here. So this rigidity theorem for infinite hexagonal packing was actually generalized for all locally finite infinite disk packing in the plane with triangular interstices. This was done when Oded was a PhD student. And then later this was generalized or for disk patterns when the disks not only are tangent, they may intersect in an angle. So this is true not just for disk packings, but also for disk patterns with overlapping. Okay. So, and there are some further methods by other mathematicians as well, Ken, who spoke here earlier, and others. Anyway, they worked under strict restriction that the radii of all packings are bounded between basically from below and from above. So, and also only C0 convergence was proved. So this was in late 80s. And I first became interested in the packing when I was a PhD student under Professor Friedman. And I think in my thesis, I proved the C1 convergence. And this can be generalized to prove C2 convergence as well. So that's how I became interested in circle packings. Now, the problems for us was, after all this work, was to generalize to arbitrary patterns. So this is actually a picture made by Oded. So what happens with arbitrary patterns, there's no restriction at all on the combinatorics. There's no bound on the valence, so a circle can be tangent to as many other circles as you like. So some circles can be really small. So, and what about the convergence of derivatives in such case? So this was the open problem in the early 90s. So first of all, how do we define derivatives in this case? Because in the regular pattern, you can do like numerical analysis. So what happens if you have a general pattern? Well, we can use the Möbius transformations. So the idea is for any two triplets of mutually tangent disks, there's a unique fractional linear transformation that sends the first triplet to the second. So basically, you take the tangency points to the tangency points. And the three tangency points determine the fractional linear transformations. Okay. So, and in particular, the map, the fractional linear transformation can be defined on the interstice. So triangular interstice. This is the shaded. Basically, that's the shaded area. Those are triangular. This is the union of triangular interstices. So we can define a map from the support of P sub n, that's the packing in the first domain, to the support of Q sub n, the packing in the second domain. So this is P sub n, that's Q sub n here. And so that the map is conformal on every triangular interstice. So because if it is conformal, so we can define the first order and the second order derivatives for the map from the support of one packing to the support of the other. But you can't define on the disks, but you can define it. You can define it on the union of interstices. So that's the derivatives we're talking about. And well, the question for you would be, what about the third order derivative? So we'll talk about that a little toward the end. So this is the main theorem. So we have a pair of domains here. So half circle, and that's, I don't know how to call that. Anyway, it's like a cone domain. So we have a packing in the first domain, P sub n, and another packing, Q sub n, that's combinatorially equivalent, the same number of circles and the same tangency relationships. Okay. So we have a map, F sub n from the support of the first packing to the support of the second packing. So that maps, as before, the maps triangular interstices to triangular interstices, and it maps the disks onto the disks of Q sub n. So F sub n is only conformal in the interstices, so it's not conformal in the disks. Okay? So it's just a continuous map. Now, those are generic assumptions. Basically, the spherical diameters of the disks are small, and also the boundary disks are very close to the boundary of the domain. And finally, a normalization condition that the map will not converge to the boundary, basically. So there's a compact subset, so a fixed point Q naught will be mapped to that subset. So not everything will tilt toward the boundary. So the condition is that a subsequence of F sub n will converge locally uniformly to a conformal homeomorphism. Okay, so this is the C0 convergence. So this does not depend on the combinatorial pattern at all. And furthermore, we have convergence of the first order and the second order derivatives. So again, those relationships are only restricted to the triangular interstices because those are not defined in the disks. They are only continuous functions, but they are defined. They are actually fractional linear transformations in the set of triangular interstices. Okay. So a corollary would be that the absolute value of the derivative of the Riemann map or of the conformal map may be approximated by the ratio of radii of the corresponding disks. It does not matter if the disk is small or big. So this has really nice control on the size of the disks. Okay, so the main points first, actually those are breaking out into 3 points. So first of all, to show that the limit map of the subsequence is a conformal map. And again, the difficulty is that there's no limit disk packing because the combinatorics is rather arbitrary. And the uniform convergence of the derivatives, first order and the second order derivatives. Okay, so actually the first 2 points can be proved by some idea in my PhD thesis, mainly, some idea there, and applying, actually that's after I learned the concept of transboundary extremal length from Oded. He taught me about the extremal length concept. Actually, he got it from Jim Cannon, some paper. Or maybe he got it before that, but eventually he eventually found that concept was also in Jim Cannon's paper. So he taught me that, and I used that idea to take care of some technical difficulty, and then I was able to, and then I wasn't able to prove number 3, and then I talked to Oded about it. Initially, he didn't believe that I had a proof. He thought my method wouldn't work. Then he said, let me think about it. And then a few days later, he came up with his own proof. So, and then we wrote a paper together on this. So certainly I was saved from writing my cumbersome proof. He wrote the whole paper basically and put my name. It was really nice for him to put my name on that. Anyway, so the argument was really simple and can be understood by any college student with some training in complex analysis. It's really a very simple idea. And so...
Where is this college?
Well, I left the colleges already, so anyway, this argument starts with this so-called fixed point lemma, which actually Ken talked about earlier, and this so-called fixed point lemma actually was used extensively in the proof of Kurbach conjecture for countably connected domains. This is another one of our journal papers, and this is a very powerful tool. And actually, I learned this fixed point lemma from Oded. He was working on the rigidity of infinite disk packings, and he was able to come up with a proof. But that proof we were able to use it for so-called circle domains as well. So that's another story. So I don't have time to talk about that here. So the fixed point index lemma was actually presented earlier by Ken, and so I would rephrase it this way here. So we have two circles, C1 and C2, in the plane that are positively oriented, and we have F1, F2 orientation preserving homomorphisms. So basically, those are two curves. F1 and F2 are basically two curves that have images that are circles. And assume that F1, F2 is never 0 on C. So basically, there's no fixed point. There's no points for no 0 point for the difference. Then the winding number of the curve F1 minus F2 around a 0 is non-negative. So this is basically the same lemma Ken was talking about earlier. And I like to mention the proofs because it's really relevant to what we're going to do next. So we have 4 cases. They bound disjointed interiors, or one is inside the other. So the case 2 and the case 3, the winding number is 1 because you can shrink a point in the smaller circle to a point. And the case 4 is a little bit more interesting, and it takes a little bit more work. So when the two circles overlap into 2 points. Anyway, so there are 2 observations. So C1 and C2 really do not need to be circles. They can be any Jordan curves as far as they intersect at most 2 points. And that's by, a simple homotopy argument. And the second is, this is not needed, but so the lemma is still valid if f sub k, so f1 and f2 are locally non-decreasing functions. They don't have to be homomorphisms. They can be of different topological degrees. They don't even have to have the same degrees. Okay, so, and here's a basic topological lemma. Actually, that's implied in Ken's talk. So this is basically, I think, in any complex analysis book, textbook. So we have a bigger curve right here. Okay, this is a bigger curve, and this is a like closed Jordan domain bounded by the bigger curve J. And we have J1, J2, J sub n big Jordan curves inside the domain, which bound mutually disjoint interiors. So those are actually boundary of disks in our applications. Okay, so they bound disjoint interiors. And A, B, the closed subset obtained from B by removing the interiors of those little curves. Okay, those little disks. So in our application, A is a union of closed triangular interstices. Okay, so just they are not disks. And all curves are positively oriented. So now G is a complex valued continuous function that is never 0 in A. So A is like the union of interstices. The disks are removed. then the winding number of the curve G around 0 of the bigger curve J around 0 is equal to the sum of winding numbers of the smaller curves around 0. That's because there's no 0 in A. Okay? And this is like a homology in dimension 1. Okay? So now what if G has some isolated zeros in the interior of A? Then you have to add up, this sum right here, you have to add up the degree of zeros of G in those isolated zeros. So that's the what I call adjusted topological lemma. So the winding number around 0 is equal to the sum of winding numbers of the curves plus the sum of degrees of zeros in the interiors of A. And in our application, G is going to be holomorphic. So the degree of 0 is always positive, at least 1. Okay? And also, those curves are going to be circles, and the G is going to be in difference of two maps, as in lemma 1. So this is the winding numbers is always non-negative in our application, because we take G to be the difference of two maps. So we're going to see that later. So I'm going to do a quick proof of the main theorem. So basically we have F sub n, which is from support of P sub n to support of Q sub n, and it maps triangular interstices conformally onto the ones of Q sub n. Okay. So F sub n, as before, is a holomorphic function in the interior of the triangular interstices. And so those are continuous. So the first step of the proof is to show that F sub n's are uniformly by Lipschitz in the interior of the domain. And this is by using so-called the Schwarz-Pick lemma for mappings of these packings. I think it first appeared in a paper by Bearden and Stephenson. And the idea is that if F contracts a bigger disk packing into a smaller one, then the derivative must be bounded by 1 in absolute value. So basically, if the disk packing is contracted from a bigger one to a smaller one. So this shows that the derivative in absolute value is bounded between those numbers when the domains are bounded domains. And the general case may be reduced to that case. Okay, so that's basically step 1. Now, step 2 is to show that the second derivative is also uniformly bounded in the interior of D. So remember, the second derivative is actually defined by the fractional linear transformations that send interstices to interstices. So basically, we have to show that the fractional linear transformations is uniformly bounded. The second derivative of the fractional linear transformation is uniformly bounded. So we take such a fractional linear transformation. So what we do is we're going to take some Jordan curve enclosing Z0. And then we change the Jordan curve a little bit. So we take a Jordan curve that contains Z0, and then we change it a little bit so that it is still contained in the union of interstices. So, and then the boundedness of the second derivative follows from the following facts. First of all, the boundedness of the zeros derivative, if you like, that's because f sub n converges by step 1. Okay? And then the boundedness of the first order derivative, so that's because f sub n is by Lipschitz. So we have boundedness of the first order derivative. And then the following lemma. So remember that f sub n is a fractional linear transformation, so it only has 3 degrees of freedom. So those two conditions 1 and 2 already place 2 conditions. So we just need one more condition to imply the boundedness of the second derivative. And basically the third condition is this. It's a topological condition right here. So the sets, the image of the Jordan curve by f sub n intersects the bounded Jordan curve of f sub n of j sub n. Remember f sub n, because it's by Lipschitz, that converges. So this is bounded. So that means that actually places a strong condition on the fractional linear transformation f sub n. Okay. So lemma 3 is the key. Now, how do we prove that? That's just by the fixed point index idea. So basically, we assume those are disjoint. So both are simple loops in the Riemann sphere. So suppose they're disjoint, but they share a common point. So this is a common point because they are identical in that interstice. That means the images share a point. Actually, they share many points. But the boundaries are disjoint, so one must be contained in another. So as a consequence, the union is actually the bigger sets. So basically, one is a subset of another. That means there's a point which is outside of the union, and we can map that point to the point at infinity by a fractional linear transformation. So we can replace the packing, image packing by LQ sub n, so the image by the linear fractional transformation. So basically we can assume those two sets are bounded sets. They are contained in the plane because they miss the point at the infinity. So now this is a technical step. So basically they are sets in the plane. Now those two maps is a complex valued map, and we know the image of the Jordan curve by 1 is in the interior, or the other one is in the interior. So the fixed point index of the difference must be 1 on that Jordan curve. But on the other hand, those two maps agree in that interstice. So they completely agree in that interstice. And the lemma 4 says that if that's the case, then the winding number around 0 is at least 3. So we get a contradiction. So the contradiction shows that the two sets must intersect each other. So now the lemma 4 basically says that the winding number of the difference is at least 3. The assumption is that the two maps agree in that interstice. Okay, so that's the only assumption, the key assumption. Because they agree in the interstice, so how are we going to talk about the difference? The difference is actually 0 in that interstice. But the idea of getting the winding number is just give this map a perturbation. So basically, we're going to talk about the following map. So we perturb f sub n by a fractional linear transformation, so that this is fixed point free on the boundary, and also achieves 3 fixed points. Okay? So this is so I'm going to skip this part. Basically, the idea is that the two maps completely agree in the interstice. So you can always give a perturbation on one of the map f sub n by a fractional linear transformation. So you'll get 3 fixed points. Okay, so G, this new G vanishes at 3 points. And that little g sub n vanishes in the interstice. So you can do a perturbation. So after the perturbation, because the map has 3 fixed points, so the fixed point index must be at least 3. So that's basically the idea here. Okay. So now, so basically at this time, we have shown the boundedness of the second order derivative. Now, because of that, we can take limits, and also we can take limits of the first order derivative, and use some kind of path integral idea, and take limits. We can show that f is differentiable, and its derivative actually is the limit of f sub n. So this is some elementary step. Now, the final step, actually this is going to be the key, and it's very simple, shows that actually the second order derivatives also converges. So this is, this uses the same lemma 4 here, the winding number idea. So the proof goes as follows. So basically, we have, okay, so I'll finish in 2 minutes. So basically, we have T sub n, that's the triangular interstice that contains a sequence of points, and f sub n are the fractional linear transformation. So we have to show that the second derivative converges to the limit, the second derivative of the limit. So we're gonna use the fixed point index. Okay, so basically we're going to use the difference. So f minus m. So we take a little curve, and we show that this oriented curve has winding number around 0 at minimum 3, and this curve J. The reason is because f and m, they agree in some interstice inside. So the winding number has to be at least 3 by lemma 4. And f minus m, we take j to be so small that this has no other 0. So that implies that the second order derivatives must be the same at p. Okay. Okay. So finally, I just want to comment a little bit on the convergence of higher order derivatives. So first of all, we don't know how to define this for arbitrary combinatorial pattern, but you can still do it for the regular packing, for the hexagonal pattern, because you can define using numerical analysis, basically ideas, to define the second order, third order derivatives, and this was actually proved to be convergent. But we don't know how to do this for higher orders. Finally, I just want to recall my last telephone call to Oded, and that was almost 6 years ago, and I was leaving for China, and he asked me why would I go to China. He said, was it due to 9/11 or something? I said no. I said maybe there's a lot of misreports in the U.S. about events in China. Actually, China is changing a lot. So, he told me that he wished to do some further work with me and maybe have some more collaboration, and he was looking forward to that. Unfortunately, that didn't realize, and I felt really at a loss when I heard about Oded's passing away last year, because we lost one of my best collaborators, actually best two. The other one was my actually PhD advisor. Anyway, I feel really sorry, and I was really grateful for the invitation of the organizing committee to give me a chance to talk here and share my experience. Okay, appreciate it. Sorry for the delay.
Are there questions? Michael?
I just wanted to recall a little bit from those early days when Oded was a NSF postdoc at UC San Diego, and John He was there finishing up his thesis, I think. And, Peter Doyle was there, and these three guys would talk about interstices all the time. I knew there was a lot of interesting stuff there. I always stayed out of those collaborations because I didn't want to have to try to say that word during the lecture. Ever in my life. I think if a better word could be found, it would open up the field to linguistically challenged people. I was always impressed by Oded's beautiful fixed point, his reliance on elementary topological arguments. He didn't want to know what the schema squares were, anything like that. The degree of the map to the circle, is where he wanted to live, and he realized that there was a lot of mathematics that would come out of understanding the degree from the circle to circle, that we didn't have to get fancy, for a few hundred years. So I saw this amazing simplicity, at the time. But I was also amazingly impressed by John He's analytic work, in that same period. In fact, I was so interested by it. I remember I told Peter Doyle once that I was thinking that I was going to study analysis seriously, and he said, "Look, you know John's phone number. That's all the analysis you'll ever need." So I stuck with apology, more or less.
Are there other questions or comments? Well, let's thank the speaker again. We'll take a quick break here of 3 minutes and then start up again. So 18 after. Okay, I'd like to introduce our third speaker, Igor Pak, who will speak on caged eggs and the rigidity of convex polyhedra. Igor?
Thank you. Thank you. No? Yes, good. Hi. So I'm actually deeply honored to be asked to speak here today. It's a really great honor, so thank you, organizer, for having me. I'm going to talk about something. I'm going to follow the same theme of circle packings, but I'm going to talk a little bit more. Actually, mostly I'm going to talk about combinatorial aspects of one particular paper, which I find extremely beautiful. So this is the result, and like probably many of you, I knew the result for many years, but I never actually, until a few years ago, I never actually opened it like a normal person, read the proof, and there are several reasons for that, but basically, to be honest, I didn't think there was a combinatorics in it. I thought there was something else. And turns out that this particular paper is a wonderful combinatorial result, and I'm going to talk a little bit about that, about what's inside the paper. So this is meant to show that here is a sphere, and there is a convex polytope, which I'm going to forget about polytope and think of just the cage, which holds the sphere. So I'm going to say that a polytope is miscribed around the sphere if actually all these edges are tangent to the sphere. Okay? You with me?
So in the picture, it's not true?
No. Okay. This is just a cage sphere. And that's how it all started. You know, people actually looked at the caged convex bodies, in particular caged spheres. But this is a very strong property, which is hard to draw. Anyway, so what Oded proved is this remarkable statement saying that for every convex polyhedron, there exists another one combinatorial equivalent which describes the sphere. No, for every So for every strictly convex body K, there is a convex polyhedron which describes that convex body. So this is a much more general result than for the sphere. And there are lots of stories behind this result. So I'm going to start with the history, and we'll see how this goes. So here is sort of a basic motivation. Many years ago, Steinitz observed that if you ask for inscribed or circumscribed polyhedra, that doesn't work. So a real, very famous Steinitz theorem says that if you have a three-connected planar graph, there exists a convex polyhedron with that graph. Okay? So this is saying that you cannot make an additional requirement of all vertices being of lying on the unit sphere. That doesn't work. Okay? Having everything midscribed, so having all edges midscribed is sort of another way of making stronger this classical Steinitz theorem. And it's sort of a miracle that it works at all. If you just look at this picture, there is no reason why this should work. So here is another less well-known motivation in geometry, but actually quite an old question that people ask. Suppose you look at all possible cages which hold the unit sphere. What would be the total length of the total sum of edge lengths that you need? And so Fesch, Todd, Bezikovich, Eggleston, and other people looked at various aspects of that. So if you want to, so in particular, if you want to say that unit sphere sits completely inside the polytope, that's known, and that has a beautiful answer. That's exactly a cube, whatever it is for a cube. But in this case, they conjectured that it's actually going to be a triangular prism, and it doesn't work. There are beta polyhedra, and in fact, the answer to this question is still open. Maybe no one thought about it for 20 years, but still, that's your chance. The answer is still open.
So the egg is allowed to stick out from
yes.
the
So for the open one. Yeah. And
so the open one is with an open cage.
yes. Yeah. So, and the real motivation kind of comes from the circle packing, and it's sort of perhaps not immediate. This is the only picture I was able to draw. So what you do is you take a midscribed polyhedron and sort of cut your sphere along the facets. What you get is you get a whole bunch of circles which lie on the sphere, and those circles form a circle packing, and then we get exactly into those pictures that you've seen in two previous talks. Lots and lots of circle packing you can obtain that way. And so in fact, in a particular case, when your convex body is sphere, that's exactly the circle packing theorem. Now, here is what doesn't work. It's sort of a strange thing to put on a slide, but you'll see it in a second. So one sort of normal way to prove the main result, let me show you the main result again, would be to take one of the standard proofs for the circle packing theorem, take the oldest one, the one that people first came up with, the most natural one, and generalize it to general convex bodies. And it's a natural way to do that, and I think it still might work. So I'm not sure why it doesn't work, actually. In a sense that you just, Oded tried, I guess, and it didn't work for him. So natural way would be to say, well, let's say your polyhedron is simplicial, so all faces are triangles. Now consider all possible position of vertices, and for every edge, let's look at the distance between that edge and the convex body. Maybe square of the distance, if you want to be. And then you do the usual things, the way people. Let's say you're generalizing Colin-Deverdier or some other variational proof of the circle packing theorem. What you do is you prove some results about this particular functional, and you're done. So you prove that it's convex, and it attains the minimum exactly on what you want. So somehow, my way of making history is that I believe Oded thought about it and didn't work, but he did figure out that you need to generalize that to work with non-simple polyhedra. Okay, so he defined the following configuration. He said, well, let's look at all possible. Let's have not just vertices positioned in the space, but both vertices and facets. Okay? So we have a bunch of points and a bunch of planes. And the right functional should have taken into account both the edges being tangent to your convex body and the vertices lying on the planes. Okay? That would be the right idea. And you would need to take some kind of sum of squares of the distances or whatever. Unclear what exactly would work. So since this approach doesn't work, or seemed not to work, I believe what Schramm did is he came up with he used, I just heard about existence of 5, 6 other proofs. So I'm not an expert on all other proofs. But he actually says in the paper, well, I looked at some other proofs, and here is something. So he came up with a proof that was motivated by another proof he did in a previous paper. But I looked at the other paper, and the motivation is sort of far-fetched. You cannot see how one proof follows from another. It's not a derivative. So what he says is basically the following. The most important part of the theorem is to prove a rigidity result. I'm gonna illustrate rigidity for this polyhedron. So let's say it's going to be caging a sphere, and I'm going to fix this triangular face. Okay. Now what Schramm says is that there is there's only one way to position all the remaining vertices so that this polyhedron cages a sphere, so that all edges are tangent. If you look at it from a combinatorial point of view, you're amazed. There is no reason for that. Why would these vertices in the corner somehow depend on this triangle in the beginning? That sounds strange. On the other hand, if you take the picture that we just did with circles, you remember this has the same 3 vertices corresponding to the 3 circles that Ken had in his talk. It's exactly the same picture. So if there was a rigidity for circle packing, there has to be rigidity here. So now what he does is basically the following. He proves the rigidity result, but he doesn't want a global result, so to speak. He wants a local result. So what happens when you change things infinitesimally? And then he thinks of that, and then he wants to use inverse function theorem. So he wants to say that this infinitesimal result is what exactly saying the Jacobian of some map is non-zero. Okay, and then you can start moving things around, and eventually, and actually, he changes the convex body itself. He changes the K, and eventually gets what he wants. So let me. So what I'm going to do is so I'm not going to cover the whole proof. The proof has sort of technical parts and which you won't like, and analytic parts that I personally don't care for, and I'm not qualified to speak about. So I'm going to give you a combinatorial part, and this is all you need from topology really for that proof. This is saying roughly the following: that if you have a map, let's say both B and A are manifolds, connected manifolds of the same dimension, and if your map is injective, continuous, and is proper, then it's actually homomorphism. It's very important that they have the same dimension, otherwise nothing works. Okay? And so what I'm going to do is I'm going to illustrate this topological principle on a completely different theorem, and then I'm going to go back and talk about how the rigidity part of Oded's proof. So here is a very simple question. This you can ask in maybe in high school. I don't know. So you want to describe. You have a fixed race starting from the origin, and you look at these polygons, and you want to describe a sequence of angles alpha I of all those polygons. What are they? Do they form any nice set? Okay, and well, you pretty quickly discover there is one linear relation, and that's this one, and there are a whole bunch of linear inequalities which they have to satisfy. So what I mean is you cannot have all those angles to be concentrating in one direction, and there's basically zero here. That's impossible. And this is where the inequalities come from. That's the only restriction. Now here is a key observation, and this is going to be sort of a rigidity result for the angles on rays. And the result is the following. If you have two polygons with the same sequence of angles, then one has to be an expansion of the other. Okay? That sounds easy enough to have a short proof, and this is the whole proof. You make one polygon to be tiny and start so it fits inside the other one, and start slowly expanding it. You expand it until it hits the bigger one. Then there's going to be one of the angles smaller than the other. Done. So this is so this is the kind of rigidity results that now you can take. Let me go back to the theorem. So now if you think about it, you have a map phi from coordinates of vertices along the rays into the angles. And that map is continuous. It's injective from what we just proved. And it's proper. That takes a little bit of thinking. And it's actually both sets are connected. And then you're done. Then from just this almost trivial rigidity result, so to speak, I would say uniqueness result, you get a result that, given the set of angles which satisfies those inequalities, there exists a polygon with vertices on the rays which have those angles. That's the idea. That's a very basic idea, and that's the same idea that Oded uses in his proof. So just to illustrate that this is angles is not a toy. This is the real theorem, and this is of Alexandrov. So this is a three-dimensional version of the same result for on the plane. Okay, where instead of angles you get curvatures of vertices, etc. His Alexandrov's idea was that he should discretize. Suppose you have a convex body, you take a curvature, project it on a unit sphere, and the question is, can you reconstruct the convex body from this Gaussian curvature? So this is a discrete version of that result. Okay? And you can actually prove the continuous version using this discrete version. All right. Now I want to present a much easier result than what Schramm had. But I'm going to show you these combinatorial tools that Schramm uses, and hopefully you can get a flavor for what exactly is in that paper. Where is the combinatorics? So I'm going to. So this is dense rigidity theorem, which people often confuse with Cauchy rigidity theorem, and in fact there are sort of neither of them implies each other because the way Cauchy stated is it's a uniqueness result, and this is an infinitesimal rigidity result. Okay, so both results are saying that if you have two polytopes, then if you have one convex polytope, then this polytope is rigid. So you cannot move vertices around so that all the edge lengths are preserved for a simplicial polytope. Now,
So why is this weaker than rigidity?
why is this weaker?
Well, it sounds like it's weaker than Cauchy because it's an infinitesimal system.
No, it's not. It's not weaker. Cauchy doesn't. Cauchy is a uniqueness result, which may be something that comes from the second order rigidity. Not everything that's unique is infinitesimally rigid.
Well, if there's one parameter deformation that didn't come from rotation, then that showed non-uniqueness.
So, correct. So let me say it again. So both Cauchy and dense rigidity theorem show you that you cannot continuously deform, but neither of them implies each other. Okay, Cauchy is a global result. So anyhow, let me define what's an infinitesimal motion. I'm going to put a velocity vector in every vertex, and I'm going to say that infinitesimal motion is if this difference between velocity vectors always orthogonal to the edge vector. Okay, and infinitesimal rigidity, if every infinitesimal motion is actually a rigid motion. All right. It's important to understand. Clear what I just said? Yeah? Or you're not following?
No, we still don't understand why it's not weaker than the global.
Cauchy's theorem implies that there's unique.
Okay.
There could be two, but they're not connected by a smooth motion. Right? So Cauchy rules that one out.
But so that's why Cauchy is not weaker, but why is
I mean, every true statement implies another. So but it's not directly, you cannot derive one from another, no. Anyhow, let me show you what exactly did Schramm do. So what I'm going to do is I'm going to weaken this property of for infinitesimal motion. I'm going to allow a larger set of possible velocities. Okay, and I'm going to so all I'm going to do is require them to have basically the same sign when projected onto the edge vector. That's a much weaker property. So if they're orthogonal, they're both orthogonal. But if one has a negative projection, then so is another. Okay. And I do that so I'm going to orient all the edges depending on this sign. Okay. So all that's important going to be the signs along the edges. And then basically what you need is a completely combinatorial result, saying that if you have any kind of vectors, if you have any kind of velocity vectors pointing from each vertex, so that one particular triangular face is fixed, then and it satisfies all these three properties, then the whole orientation, there is no orientation. All edges are not oriented. We have basically zeros everywhere. The whole all velocity vectors become zero. That's what you prove. Okay, and that's a combinatorial result. So this is almost directly from Schramm's paper. What he does is he looks at orientations and he defines just almost like in the proof of Cauchy, but somewhat different also. He defines these full inversions and half inversions. So in particular, so if you have a edge oriented into the vertex and another oriented out of the vertex, that's going to be two halves. That's one full inversion. But you're going to have lots of unoriented edges. So this is unoriented edge, and this and you get half inversion on each side. All right. So that's what he does. And then a little combinatorial observation is this lemma 1, which you can obtain by just basically looking at all possibilities, if you like. That this set of Schramm's inversions is actually very good in the sense that if there is at least one light vertex in a triangle, then the whole triangle has at least one inversion. And line vertex, think of line vertex as the one that's actually moved by those velocity vectors. So that's believe it or not, that's half of the proof. So here is another half of the proof. So previously we bounded the number of inversions from below. Now we're going to bound them from above by making the following observation. Instead of looking at triangles, I'm going to look at the vertices. And it turns out that if you start looking at the vertices, there are at most two inversions around every live vertex. And again, you can just consider all the possibilities in each vertex. So I should probably point out that you cannot have edge going in, out, simply because there is this edge. All these edges are convex, so let's say they're pointing towards the blackboard. Then projection of velocity vector has to be sort of pointing in one direction. You cannot have them alternating. And that's all you need to do for the lemma 2, to just observe that. And the rest is Euler formula and double counting argument. That's how the proof goes. And so I know you want to go to lunch. Let's see. So let me just say that this is. So I'll finish with an anecdote from that paper. So I actually looked at all these details, and at some point I got really confused because Oded spends like 2 paragraphs summing some angles, calculating some formula, and later on I realized that that's Euler's formula. So in addition to proving many other things, including dense rigidity theorem, he proves Euler's formula, using a non-standard new proof of Euler's formula. Oh, okay, so that is it. Thank you.
Are there any questions or comments?
Isn't this proof very similar to
Not at all. Completely different. Dan calculated a determinant as a product of. It's a beautiful. Dan had a beautiful proof, 1915. I read it very carefully. Let me plug it. It's also in my book. Or in German. Choose your language.
No other questions? If If not, let's thank the speaker.
Thank you.